All right, so let's get back to the problem here. So we have our initial concentration is 6.0 molar. That's our stock solution. We're trying to figure out what volume of that stock solution do we need. We know that we want to end up with this. We want to end up with a solution that is 0.15 molar, and we want to end up with 0.80 liters of it. So let's solve for V1. And so we're going to rearrange our formula. V1 is going to be equal to M2 times V2 divided by M1. And so M2 times V2, so let's take 0.15 molar. We'll multiply that by 0.80 liters, and we'll divide that by our M1, which is 6.0 molar, like that. And when we punch that into our calculator, let me double check here. 0.15 times 0.8 divided by 6. There we go. We end up with 0.020 liters. Okay, so that would be the volume. If you multiply that by 1,000, you get the number of milliliters, which would be the same thing as 20 milliliters. So what you would do is you'd go to your stock solution, your more concentrated solution. You'd measure out 20 milliliters and dilute it up to 800 milliliters, and there you go. Now you've got 800 milliliters of your 0.15 molar solution. Give a thumbs up if you follow me on that one. I want to do some more lecturing about some cool concepts. All right. Well, let's keep moving along here. We got 2 more hours, so just getting started here. Kidding. All right, there we go. I had the solution in there, but I don't like to look at the answers. Let's think about something here. Hey, here's a reaction that you might have done in the lab already, and if you haven't, I'm sure you'll get a chance if you're taking Organic Chemistry 1 lab, okay? All right. This is a pretty neat reaction. It says here, writing equations for aqueous ionic reactions. You're starting out with a solution of silver nitrate. Okay, so this one here, this is silver nitrate. Come on. Silver nitrate, and then over here, we have a solution of sodium dichromate. This is just showing you what it looks like at the atomic level, right? You have your ions dissociated, you get your silver, your nitrate, your chromates, your sodiums, right? You can see all those ions. So what happens is you put all of those ions in solution, right? When you mix these two, okay, you mix those two, think about it. Now you've got a mixture of what? You've got a mixture of silver ions, sodium ions, nitrate ions, and chromate ions. So they can all kind of interact with each other. And what happens is if a silver ion comes near a chromate ion, you end up forming a solid, this like red solid right here, okay? That's called silver chromate. And you notice how at the end of silver chromate, it doesn't say aqueous, it says S, right? S is equal to solid, or that's what the precipitate is. So that's what this is right here. That is a solid, okay? So a solid actually precipitates or crashes out of solution, and then you're left over with ions that just didn't do diddly squat. The sodium and the nitrate, they're still in solution. Okay, we call those spectator ions. They're kind of like ions that like to wear cashmere sweaters, nodding about their necks, swing a tennis racket, you know, summers at Kennebunkport. They don't do anything, okay? They just stand there and watch, okay? So they are not participating in the reaction. So the first equation, now, I know I'm talking pretty quickly because I'm excited about this. I think this is very cool. You start out here with what's called a molecular equation. That's where you write everything out in dirty detail, okay? Silver nitrate, the sodium chromate gives you silver chromate and sodium nitrate. You're basically swapping the silver with the chromate and the sodium with the nitrate. We call that a double displacement reaction, or we can call that a metathesis reaction, kind of a sassy name, okay? Now, you get the next option, which is the total ionic equation. I abbreviate molecular equation, ME. Total ionic equation, I call it the TIE. You break everything that's ionic apart into its ions. So silver nitrate, break apart into its ions. Sodium chromate, break that apart into its ions, okay? Now, pay very close attention. The silver chromate does not get broken apart into its ions. Why not? Because it's not aqueous. It's a solid, right? Okay? It's a solid. whereas the sodium nitrate does get broken apart into its ions. So the answer is, if something says AQ by it, you write it as ions. Okay? Then what you can do is you remove, oops, my eraser. You can remove everything that's a spectator ion. So all these ions over here, the nitrate, the sodium, the nitrate, you write what's left over. Everything that's not a spectator ion, and we call that the net ionic equation. It's a beautiful thing. And if you're like, well, hey, Mr. Dion, the net ionic equation looks to me like that's the only thing that's really happening. The rest is just kind of sitting around spectating. You're absolutely right. And you would be 100% correct. So you've got to know the difference between a molecular equation, a total ionic equation, and the net ionic equation. Look, let me just stop here for a minute, and I'll let you take a break and listen to me talk about chemistry. I know that students still, probably at this point in the class, some of you, not everybody, but some people find, nomenclature, like takes a while for me to get nomenclature down pat. But look, if I can encourage you, never, ever, ever give up on nomenclature. Never, just always be relentless. And why? Because nomenclature is going to come up in just about every lecture from now until December. Okay? So remember, if you're like, oh, I don't feel like spending all that time making flashcards and watching videos and this and that and practice, I promise it will be time well spent. Okay? You will never look back on the final exam and be like, boy, I wish I hadn't spent all that time learning those names. You'll be like, dang, that was the right thing to do. It's going to be handy in general chemistry too. You know what? I'm interested in taking organic chemistry. It's going to be handy then. Anything to do with chemistry, nomenclature is going to be great. Yeah, somebody says, I have all the flashcards if anybody needs help. Some of my students, I don't know if I told you this story or not, but I'll tell it to you very quickly. This isn't a Gen Chem thing, but in organic chemistry, we have a similar thing where we learn a lot of different reactions, and students have a hard time sometimes remembering all of the different reactions. So sometimes over the course of the summer, they'll forget most of the reactions and they won't remember them. And maybe a couple of semesters ago, I came back after the summer, they came back, I should say, and there was one gal in the class, and she knew every reaction that we had learned before in the spring semester. And I asked her, I was like, how do you know all the reactions, Madison? And she's like, good question. And what she did is she said those kind of big key rings that you can buy there? She put all these flashcards on a key ring with all the different reactions. And then she worked at a grocery store, like, I don't know what she did, but maybe working the cash or something. And she said, whenever I had a spare second, I would pull those flashcards out of my pocket of my smock or whatever and just look at it quickly. And she said, by the end of the summer, I just knew every single one. Like, there was 100 of them in there, but I knew them all off by heart. So, repetition is the best way to learn something. Anyhow, I've already covered total ionic equation and spectator ions. I've covered net ionic equations. Now I want to talk about precipitation reactions, and I've got some great news for you guys. I have a video that covers this section in detail. So video on my YouTube channel. I mean, if you guys could see the dump trucks of money that they're backing up to my house for these YouTube videos. Anyhow, so I have a whole video where I cover precipitation reactions. And I wanted to just point out something that on the schedule, if you paid close attention, that it says that today and tomorrow and maybe a little bit on Friday, it says today and Friday and a little bit on Monday, we're going to be looking at this part of the book, chapter 4. I just want to point out that we're also going to be looking at some of these concepts again later on. So that's why there's a section, chapter 4, part 1 and part 2 kind of thing. Anyhow, I just want to talk to you for a few seconds. We've got 8 minutes left, okay? That's more than enough time to talk about what's called a precipitation reaction, because you've already looked at a precipitation reaction. It was what was on the last slide. Let me show you what's going on here. Oops, I just want to find something on my slides. Where was it? Oh, I don't know. Anyhow, a precipitation reaction, okay, is when you take two soluble ionic compounds and you end up with an insoluble product. So remember, if it's soluble, it's going to say AQ next to it. If it's insoluble, it's going to say solid next to it like that. When it's solid, when you form a solid compound, we call that a precipitate. I like to abbreviate it PPT because I can't write out precipitate. A precipitate forms through the net removal of ions from solution. It's possible for more than one precipitate to form, such as in such a reaction. That's you. Sometimes I don't think we look at a whole lot of reactions where we form more than one precipitate, but the whole idea is nothing more than this. Look at this beautiful homogeneous solution. Look at this beautiful homogeneous solution. You mix the two of them, and all of a sudden you get a precipitate. Okay, so that might be, it's probably like lead iodide or something, because lead iodide is yellow anyhow. All right, so that's what precipitation is. Look, this is what's happening at the molecular level, okay? If you mix calcium chloride, you can buy it probably at, Ace Hardware. Where's my pen? Yeah. Calcium chloride. Okay, calcium chloride dissolves in water, no problem. So it's aqueous. If you mix that with sodium fluoride, metal, non-metal, ionic, goes into solution. What are you going to have when you mix these two things? You're going to have an aqueous solution of what? Calcium ions, chloride ions, sodium ions, and fluoride ions. Now, all four of those ions can come close to each other, but it just so happens that if a calcium and a fluoride ion, if they come close to each other, what they do is they form this right here. They form a solid, okay? And that is called calcium fluoride, and it is a solid, okay? So we write CaF2 solid. Now, if you're way ahead of me, you might be asking, well, Mr. Dion, how do you know it's a solid? How do you know it's not AQ? There's a good way to figure that out, and I'll tell you in a little bit, okay? And then you're left over with sodium chloride. That's your molecular equation, the first one here. You write out all the ions, and you get your total ionic equation. Then you write out your net ionic equation. You cancel out the spectator ions, the sodium and the chloride, right? They didn't do anything anyway. Okay, give me a thumbs up if you follow me thus far on a precipitation reaction. Just this far. Let's see here. Scroll down. Okay, good. Thank you, Blake, Matthew, Bryn. Wonderful. Excellent. Okay. Let's see here. So to answer your question that I asked for you, which is, how do you know when it's going to be a precipitate? First, you got to look at all the ions. Okay, you look at all of them. You look at all the possible combinations. Then you use a set of rules. You're like, oh man, more rules. Yeah, you use some more rules. And if you form something that's insoluble, you end up with precipitate, which is a solid. You're like, where do I get these rules? Oh, good grief. You get them from this table right here. Okay, so let's say you had, the two compounds that we looked at, which was calcium fluoride and sodium chloride. Let me show you how you use the table. Let's analyze sodium chloride first, NaCl. Okay, we'll just think about that. It says here, soluble ionic compounds. It says all common compounds of group 1A. Hey, look, sodium is in group 1A. Then it says insoluble exceptions, none. So that tells you that sodium chloride is going to be, aqueous, right? It's going to go into solution. Now, calcium fluoride, let's see about that one. If you go down, oops, I didn't mean to do all that, but anyhow, I did. Where was I? Calcium fluoride. Okay. Where would I find calcium? So there's nothing here about calcium. There's nothing here about calcium. Common nitrates, no. Common chlorides, bromides. Oh, look at this. It says here, soluble ionic compounds. Hey, it says all common fluorides. Hey, calcium fluoride, that's a fluoride. Let me see. Insoluble exceptions. Lead fluoride or lead 2 fluoride and fluorides of group 2A. Hey, where's calcium? Calcium comes from group 2A. Therefore, this is going to be insoluble. Now, I haven't gone over the whole table. We don't have a lot of time left. Give me a thumbs up if you think you could figure out the rest of the table. Cha or no? All right. Okay. Violet says she could. Okay. A couple of people think they could. Okay. The table's not meant to be anything mind-boggling or whatever. But we'll take some more look at it. You know what? We got time. What else? Solubility rules, lead iodide. Oh man, there's so much cool stuff in this chapter. I love this chapter. It is real. Sorry, Mr. Dion's just looking through here for his own personal edification. I can't wait for Friday. Super pumped. Super pumped to talk about the rest of this chapter with you guys. Awesome, awesome chapter. Does anybody find this chapter like one of the most enjoyable chapters they've read thus far? I find that in chemistry, once you really start to understand nomenclature, that's when the subject,